In example 2, we found the general solution of the linear system y prime equals 3, negative 6, negative 3, 0 times y in terms of constants c1 and c2 to be y equals c1 e to the negative 3t times 1, 1 plus c2 e to the 6t times negative 2, 1. Recall that the phase portrait shows the solutions of the system of differential equations in the xy plane. Let's sketch the phase portrait using the general solution that we found, instead of from a direction field as we did in the beginning. To start, we know that when c2 equals 0, the solution is simply y1 of t, which is c1 e to the negative 3t times the vector 1, 1. And similarly, when c1 is 0, the solution is y2 of t equal to c2 e to the 6t times negative 2, 1. Since these solutions give scalar multiples of the eigenvectors, they give us the straight line solutions. The scalar multiple here is c1 e to the negative 3t for y1 and c2 e to the 6t for y2. Now, as we move along y1, as t increases up to infinity, e to the negative 3t is going to 0. So we get a smaller and smaller scalar multiple of our eigenvector 1, 1. And thus y1 equal to that scalar multiple times 1, 1 goes to the origin along that vector 1, 1. We indicate this on our phase portrait with an arrow that points in the direction of our solution as t increases. Now along our other straight line solution, y2, as t goes off to infinity, e to the 6t goes to infinity as well. And thus y2 becomes a larger and larger scalar multiple of our eigenvector v2. So we put lines going out of the origin along our red line, indicating that as t increases, our straight line solutions will move away from the origin along that line. So we've seen what happens along our straight line solutions as t increases. But what about the curves of other solutions where c1 is not 0 and c2 is not 0? Remember, these straight line solutions are just special cases of the general solution. To understand what happens for a generic solution where neither of them are 0, let's just pick some generic point that's on neither of the straight line solutions and think about what happens as t increases off to infinity. Now, we know our solution fits the form of our general solution and is a linear combination of y1 and y2. And as t goes to infinity, we know that y1 goes to 0 because of the negative exponent negative 3t. And thus y of t gets asymptotically close to the other term, c2 e to the 6t times negative 2, 1. In other words, a scalar multiple of v2. So drawing this in through our point, we get a solution that gets asymptotically close to our red straight line solution. And conversely, on the other side, as t goes to negative infinity, y of t gets asymptotically close to c1 e to the negative 3t times 1, 1. This is because as t goes to negative infinity, e to the 6t will go to 0, and that red term will drop out, leaving us with a scalar multiple of 1, 1. So the rest of our curve will get asymptotically close to the blue straight line solution as we move opposite the direction of the arrow. Because remember here, we're looking as t decreases to negative infinity, and the arrow points in the direction as t increases. Now, there was nothing special about the point that we picked for our argument here, other than the fact that it wasn't on either of our straight line solutions. So for any starting point we pick, the solution should tend towards our red straight line solution as t increases, and towards our blue straight line solution as t decreases. Typically in a phase portrait, we'll draw in the straight line solutions as well as one solution in each region bound by the straightline solutions. This phase portrait gives us a graphical representation of what our solutions look like in the xy plane.